-1. All right, hi, welcome back to Mac 234 Multivariable Calculus. I'm still your host, Steve Dragoo. Today, this is the last unit we're covering before exam 2. Right, so exam 2 is this week. It's on Thursday, which means in our next class, we'll be doing a review session. That'll just cover everything that you need to know for this second exam. And like I said, this is the last topic we've got to cover before we get there. And it's kind of an extension of Friday's class. But that chapter is 16.3, or I guess maybe section 16.3. We're looking at the fundamental theorem for line integrals. And before I dive too far into the new stuff, don't want to go at it right away. Yeah, might as well. From section 16.1, the thing that I said we were gonna need again, and it's gonna be pretty important, was this box on screen right here, where we're looking at conservative vector fields. That's going to be our big key idea that's going to be important to us in the fundamental theorem for line integrals. And basically what it says is that a vector field is conservative if it is the result of some gradient. All right, so if I take a regular old scalar function, call it f, maybe something like xyz plus y squared, and take the gradient of that function, I get the field seen over in the lower right part of that box. Looking down here right here. That field there. We're going to say that that thing is a conservative vector field, again, because there is a function that it is the gradient of. That's a unique property of these conservative vector fields. Most fields do not follow this principle. But if we have one that does, we can say some rather nice things about moving through the field. So we call that generating function the potential function. That's our little f, the thing that created the field, or the thing that served as the base for the gradient to create the field. And we're going to look at some unique properties of those fields today. So let's go do some of that. Oh, come on. Don't be like that. There we go. So first, I'll look at an example of what might go on in these fields, which is to look at calculating some line integrals. In particular, I want to integrate the line integral of a field, 2x, 2y. And I'm going to look at taking integrals along several different paths. Right, so in the last section, we looked at integrating along these curved lines through space, and we needed some sort of a parameterization. But if we had that parameterization, we could just look at f.dr and integrate that thing over our bounds. So for that first one, I've just got the parameterization tt. That's my blue parameterization. It's just a straight line that goes from 0, 0 to 1, 1. Found its tangent vector. There we go. Tangent vector is 1, 1. Plugged it into my line integral calculation, and I got a result of 2. Then I did the same thing for the green line, and I got a result of 2. And then I did the same thing for the orange line, and lo and behold, even with a terrifying looking trig function in there, I got 2 again. And if I really wanted to put the effort into parameterizing that rather insane looking zigzag that keeps bouncing back and forth and is made up of a ton of tiny little line segments, and calculated its integral along that path, just take my word for it, you're gonna get 2. So, what's going on here? Why do all of these integrals come out to the same value? And it turns out that is going to be a property of a conservative vector field. We have what we call path independence, which means if we're looking at calculating a line integral between 2 points, and the path we take to get there doesn't matter, we get the same result no matter what path we take to get between 2 points, we'd call that particular line integral to be path independent. And that is a property of conservative vector fields. So if our field's conservative, again, if it's the result of some scalar, then I can evaluate a line integral by choosing the nicest possible path between the 2 points, since they'll all work out to the same thing. And I want to say below here, yeah, looking back at the field that we were looking at integrating in the first example, which was 2x, 2y, I think I could relatively confidently say that that field, 2x, 2y, is the result of taking the gradient of x squared plus y squared. Maybe even plus some other constant value whose derivative is going to end up being 0. So again, I can just check it by inspection here. Just do the gradient on that function I provided, x squared plus y squared. Its gradient should be 2x plus 0 and 0 plus 2y. Or just 2x, 2y, exactly the field I came from. So we're going to be looking at trying to come up with these original potential functions, because if we have those, turns out calculating some of these integrals is going to be very, very nice. But a couple of quick definitions that we gotta get out of the way first. Simple closed curves and simply connected regions. I think it's probably easiest to understand simply connected by looking at things that are not simply connected. So figure 7 over there in the lower right. Right, that top region is simply connected. Nice little mean structure. All of the other things not simply connected. The one on the right, where I've got 2 halves of a circle, I mean, that thing's not connected. So how could it be simply connected? It's in 2 separate pieces. But also be simply connected, we need to not have any holes in the middle of our region. So for the most part, as long as we don't have any holes and we don't have any weird spots where our domain ends up being disconnected, we'll call it simply connected. For the most part, we're just going to be looking at simply connected regions as we try to run through our integrations. And then if I want a simple closed curve, well, closed just means that it's a loop. It comes back to itself. So an open curve or a not closed curve is just sort of like a, I don't know, piece of spaghetti. It's simple and closed if it connects back to itself, and also it doesn't twist anywhere. Right? We don't want it to intersect itself before it comes back to closing itself. So we'll need those pieces as we go because we really want to be applying our new theorems to simply connected regions. Because then the formal definition of simply connected involves using simple closed curves. I think in particular, we've got to say that every simple closed curve stays entirely within our region is a definition that we're going to use there. But again, I think from the 2 pictures, you can get a good enough idea of what we're after. But there's more reading there if you want to go more in depth on that. So the real thing we're here for, the fundamental theorem for line integrals, which says, what's on screen right now? If I have a conservative vector field and my domain is a simply connected region, then if I want to evaluate the line integral between 2 points, remember that if I'm on a conservative vector field, I have path independence, so the route I take to get there doesn't matter. And in fact, I can just look at my 2 endpoints and nothing else to evaluate that integral. Notice here that if I just take my 2 points, which were 1, 1 and 0, 0, my end was 1, 1, my start was 0, 0, plug them into the function that we generated, that potential function, just take their difference, and I get 2, the same answer I was getting every other time. Which is going to lead us into our fundamental theorem, which says that if we have that conservative vector field, then the line integral along that curve, or whatever curve we want, through our conservative vector field is just equal to f of b minus f of a, which should hopefully remind you of the fundamental theorem of calculus. Being the first thing that we looked at once we got into integration all the way back in calculus 1, if I integrate f prime of x dx from a to b, that's just f of b minus f of a. Fundamental theorem for line integrals is basically saying that exact same thing. There are a couple of small nuances there, but for the most part, it's going to be easiest if we just think about it as the fundamental theorem of calculus, but just applying it to line integrals. So what all do we need? Yep. So we need our continuous gradient vector field. Our domain needs to contain our curve. Some fancy things we'll just toss in there. But one of the major differences between the fundamental theorem of calculus and the fundamental theorem for line integrals are going to be the a and b values. Right, when we did the fundamental theorem of calculus, a and b were just numbers, or now we would call them scalars. And here in the fundamental theorem for line integrals, a and b are points. It's got to be some xy point that we can plug into our function. Cool. And one sort of addition to tack onto our fundamental theorem that we have here, in particular, going back to path independence, we can also say that some line integral is path independent if and only if that line integral is equal to 0 for every closed path. Which I think is a pretty natural idea to happen upon. So let me just go sketch out why I think that's going to be the case. Say I have some point that I'm going to start my line integral at. I'll call it A. And I'm going to move along some path. Kind of doesn't really matter what the path looks like, except that I know this thing should be closed, which means I need to come back to the same point by the time I'm done. That's a closed path. All closed paths have to be a loop. My beginning and my end need to be the same point, which means if I apply the fundamental theorem for line integrals, f of b minus f of a, well, each of those values should be the same thing, since b and a are the same point. I'd just get f of a minus itself, or maybe f of b minus itself, depending on how you want to think about it. So my result should be 0, as long as my fundamental theorem holds. Which it's going to, again, as long as I have a conservative vector field, again, meaning that all of my line integrals are path independent. But all right. Enough of the theory stuff. Oh, well, okay, fine. Maybe one more step before I'm going to say that. How do we know if something is conservative? Do that part first, and then we'll go do an integral or an example. There it is. I knew it was on this page. Let's figure out about the last step. I'm getting a little ahead of myself. So if I want to check to see if a field is conservative, right? We already have its definition, which is that it is the result of some gradient. But just sort of saying that definition and actually being able to check if a field is conservative might be two different things. So the thing that we want to have is, again, what you see on screen right here. If my field is PQ, P being the X component, Q being the Y component of that field, and where P and Q are going to be functions of X and Y, we and those derivatives exist. Just get to the punchline here. Qx should be equal to Py. If my field's conservative, I should have that. Q partial x is equal to P partial y. Or alternatively, Q partial x minus P partial y is equal to 0. I think is a pretty nice extension of that, right? If I just subtract the P partial y over to the other side. That definition will come up more when I start trying to apply this thing to 3 dimensions, which we're kind of going to look at the end of today. But again, Q partial x should be equal to P partial y. But notice where those partial derivatives end up. Because I think they're the opposite of what you'd expect. Right? Q was the y component. right, colored in yellow up there. But I'm going to take its x partial derivative. Similarly, P was the x component of the field, but I'm going to take its y partial. So I'm doing the opposite derivative of the position those two components are located in. So that's element number one to notice about the check that we're doing here. And it's probably worth explaining why I want to do that. Let me just pop over here for a second. So again, if I'm trying to check to see if this field is conservative, then I know that the field should be the result of some gradient, which means P and Q really have more information stuck in there than just this one's P and that one's Q. In particular, P and Q are supposed to already represent partial derivatives. So when I'm doing the check of Q partial X being equal to P partial Y, those two new derivatives I'm adding in really make this thing a second order derivative, because I'm assuming that they are already partial derivatives. P being the X partial and Q being the Y partial, because when I take the gradient, they just go in order. So when I'm looking at Q partial X, that's really F partial Y partial X. Notice that bit in yellow. And when I'm looking at P partial Y, P is already F partial X, I hope. So P partial Y is really F partial X partial Y. So the check I have in the end is just seeing if the two mixed second order derivatives are equal. I'm checking to see if Fyx is equal to Fxy. That's the idea there. Because if I find that they're not equal in that final result, that means that P and Q were not F partial X and F partial Y to begin with. Because we know, as long as we have nice looking functions, which is all that we're looking at, that the order I take my two partial derivatives in shouldn't matter. Right? F partial Y partial X should be equal to F partial X partial Y. So that's our conservative field check here. We're looking at the opposite order partial derivatives on P and Q, but we're doing it in the opposite order because we're expecting those two pieces to already be partial derivatives. So I just need to do the partial derivative that hasn't been done already to check that they're equal. All right, so that's our plan. Now, let's go do an example. So, all right. Considering the vector field e to the x cosine y plus y and x minus e to the x sine y plus 3, show that that field is conservative. So let's go maybe do that. So here's my P, here's my Q. And I'll start just checking some pieces. Let's take P partial Y. Stop it. P partial Y, there we go. Well, if I take a derivative of the purple one with respect to y, again, remember I'm doing these in the opposite order. The derivative of cosine is negative sine. So I've got negative e to the x sine y plus 1. If I do the purple one, p for purple, doing its partial derivative with respect to y, I get that result. Move over to the q component, the y component. I need the x partial on that one, because I'm assuming that it hasn't had its x partial yet. And take its derivative, I get 1 minus e to the x sine y plus 0. Right, maybe I'll just add that plus 0 and derivative of 3 is 0. And now if I just compare those two pieces, if I compare qx and py, I think I can see that they're equal. Right, negative e to the x sine y plus 1 and 1 minus e to the x sine y, those are the same equation. Oh, and I'm gonna run out of space here really, really quick. So let me just reorganize this slightly. Those two things go over there. This is part A, and now let's go look at part B. So I need to find a potential function that shows that these two things are going to be the result of a gradient of some kind. And for right now, let me go over just summoning a function out of somewhere because I want to go into a little bit more detail about where they might be coming from in a moment. I want to try, yeah, sure. Let's just try it this way and we'll work our way up to it. So if I'm looking at that first bit, the purple derivative part. Is this yeah. So the purple part, I want it to be the derivative of something, and I need it to have been an x derivative. So e to the x cosine y is the derivative of e to the x cosine y. That won't have changed. If I have a plus y, that needed to have come from x times y, taking its partial derivative there. And that's everything from the purple set. If I'm looking at the yellow set, again, it should be the y derivative of something. So x must have come from xy, which is already in the function. Minus e to the x sine y. That should have come from the derivative of e to the x cosine y, which is already in the function. And that plus 3 should have been plus 3y. That's not in there yet, so I'm going to add it in. I'm going to argue that that's my original function. A way I might have gotten to there, I just kind of set that out of the way, is to just integrate p and q. If I integrate p dx, again, I want to integrate that purple set with respect to x. I get the integral of e to the x is just e to the x. But again, that cosine function, I'm treating it like it's a constant because it's got y in it. Plus, the integral of y is just x times y. And normally here, this is where we would write plus c, which I'm still going to write in. But c is more than just a constant this time. Right, if I'm doing an integral of that thing with respect to x, then my constant should gather up any constant that I might have had, but also any other term I might have treated like a constant. Which means my plus c term really depends on y. So it's going to collect all of my constant terms, if I have any, and all of my terms that depend only on y, because I wouldn't expect them to show up in an x partial, since I would have treated it like it was a constant, so its derivative would end up being 0. If I go to do the same thing to the q side of things, integral of q dy, well, what do we get? The integral of x should go to xy. The integral of sine y should be negative cosine y. So I have a double negative, which becomes positive. e to the x I'm treating like it's a constant multiple. Integral of sine was cosine. And what's up next? I've got a plus 3y. Right? Integral of 3 should be 3y. And again, I'm going to add in a plus c to the end of that integral. But just like last time, I'm going to say that thing is going to be a plus cx. Right? It's going to be all of my constant terms and all of my terms that depend only on x. And finally, I want to combine those two parts back into my original function, my potential function, to come up with this function here, e to the x cosine y plus xy plus 3y. That's at least what I'm going to claim that we get here. What else to be said about that? I could double check this function right here. I could take its gradient and see that I come back to the original function that's there. But maybe a slightly better explanation of how I put all of these pieces together. Right, because I see that I have an e to the x cosine y in both of my two integrals. But then I only want it to show up once in my potential function. Same thing with xy. I see that it's present in both of my two integrals, but it only shows up once down in the original function. And then lastly, I've got that plus 3y that I need to add in. Right, so I don't want to double up the pieces that show up in both of these two integrals, because any term that depends on both x and y, I expect to show up in both partial derivatives, since there's going to be an element that survives out of each of those terms. Right, so xy is a really good example. When I do the x partial, I expect that term to just show up as y, since the derivative of x is 1. And when I do that derivative with respect to y, partial y on xy, I expect that to show up as just x, because now the derivative of y is 1, so x times 1, meaning it ought to show up in each piece. But I don't want to add it to my potential function twice, because then I'd get plus 2xy, and all of a sudden I'd be seeing 2y and 2x show up in my two partial derivatives, which isn't what I want. Right? I want it to just show up as the derivative of xy in each piece. So when I'm looking at taking the combination of those two integrals, I'm thinking of it more as the union of the two things rather than the two results added together. I'm taking out every unique term and plopping it into my potential function. I think we'll look at some more methods again in a second. But that got us to part C, which I think we now want to just evaluate this integral in some way. So assume C is the curve parameterized by r of t is t, sine t, and we're going to go from 0 to 1. So if I just look at r of 0 and r of 1, I'll get the points 0, 0, and 1 sine 1. Those are my 2 points. I'm turning my parameterization back into a couple of xy points. Because the fundamental theorem, the whole reason we've been doing all of this, says that this line integral, f dot dr, along C, doesn't actually matter what path I take. So I don't need to parameterize that whole thing. I could instead just look at f of 1 sine 1. 1 sine 1. Sine 1 minus f of 0, 0. And just plug in my xy points to the function that we generated. So this thing looks like plugging in 1 and sine 1 for x and y. That'll be e to the 1 times the cosine of sine of 1. An odd kind of function there. But then I want to add to that x times y plus 3y. So 1 times y plus 3y. I'll, for the sake of brevity, call that 4, since 1 plus 3 will be 4, times sine of 1. Minus, I always want f of b minus f of a, plugging in the other points. E to the 0 is 1, and cosine of 0 is also 1. So 1 times 1 is 1, plus 1 times 0 times 0 is 0, plus 3 times 0 is also 0. So I get that as my result. So again, we think that this is hopefully nicer than having to plug in my parameterization, finding a tangent vector of that parameterization, and then integrating that thing. Instead, I'm just finding the potential function and plugging in the endpoints. Right. In the second example, a more robust process for solving whether or not I have a potential function. How am I going to get there? So here's a 3-step process that will work to get us there, though I think it's a little cumbersome. So right after this, we're going to look at a slightly better way as well. So first, determining that the field is conservative. Mark off my P and my Q, just to keep myself thinking about what it is I'm doing. I need P partial Y, which is 3 plus 2x. But look at the purple half. I also need Q partial X. So look at the Y component. Do the X partial. I am going to get 2x, and I think that someone's probably about to tell me that I've done something really strange, right? I'm pretty sure the derivative of 3, regardless of whether it's an X or a Y partial, is 0. So let's just fix that real quick. Over on the other side, the derivative of negative 3y squared. Remember, that's an X partial, so it's also 0. So in the end, I've got 2x equals 2x. So this thing is a conservative field. Right, Py and Qx are equal. Step 1 done. All right. Following the new step-by-step process for trying to solve for our potential function. So there's nothing special about integrating P dx first. This process is entirely reversible. I could do the integral of Q dy first, then find f plus g of x, and then start trying to solve for g of x by differentiating the thing, solving for g prime, then reintegrating it to figure out what that element is. But the text usually likes doing the x parts first, so that's why we're going to do it this way. So in this 3-part process, again, I'm looking to find the potential function, which again, I know PQ should be the gradient. I'm trying to undo that, which means taking derivatives. So I am going to integrate Come back here. 3 plus 2xy. 2xy. Dx. And I'll get a result over here of 3x plus x squared y plus, right now I'm going to call it g of y. Because I know that if I do an x integral, whatever other part I might have, the leftover bits, could be constant values, or they could be terms that I treated as constant values, meaning a function that depends only on y. And I think if we look back over at the q partial, or the q partial derivative, which is supposed to be the y partial derivative, there is a bit that depends only on y. So I'm expecting to pick something up if I go this route. So now that I've done that, I need to take the derivative of that thing. 3x plus x squared y plus g of y. Take its derivative with respect to y, and I'm going to set it equal to q. Since q is supposed to be the y partial derivative of this function anyway. So if I do that y partial, I am going to get 0 plus x squared plus g prime of y, and that thing is equal to x squared minus 3y squared. Start solving this thing for g prime of y. I'll know that I actually have a solution that makes sense if the other side only has y's left. Or it could be 0 over there, could be a constant. I suppose more particularly, if I've solved for g prime of y, I'm not expecting to see any more x's. I think this is a function only on y. But I found that over here, g prime of y is negative 3y squared. So then I'm going to come back up and integrate that thing. Integrate negative 3y squared dy to get negative 3y. Nope. Negative 3y cubed over 3, which is just negative y cubed. There we go. This thing is g of y. We just kind of track some things through our problem. This guy and this guy, I expect to be the same. Also, when I go to build my potential function, which I think I'll have space to do right here, I'm going to get 3x plus x squared y minus y cubed. And I'll build it in this particular case just from my original integral on p, which said it was 3x plus x squared y plus whatever g of y might be, and then I spent some effort trying to solve for g of y. So I just replaced that with the minus y cubed. But again, I want to talk about this function a little bit more in a second to maybe say that there could have been a faster way to get there. Or at least I think it's a faster way, just a slightly different way that's less formulaic, but I think kind of holds all of its ideas better together a little bit better. Yeah. So if I now want to evaluate this integral where the curve is given by e to the t sine t, e to the t cosine t, evaluating from 0 to pi, well, I don't really want to do all that. That's the whole point in finding this potential function. Instead of needing to integrate that whole mess, I just want to look at that curve at its endpoints. So I want to look at r of 0, and I want to look at r of pi. Because I'm going to turn these back into xy points. If I plug in 0 for x and y, E to the 0 is 1. Sine of 0 is 0. And then e to the 0 is 1. And cosine of 0 is 1. So 1 times 1 to that second half. For e to the pi, well, again, I'll get 0 for the x component because sine of 0 is still 0. Or sine of pi is still 0, excuse me. But cosine of pi is negative 1. So this will be negative e to the pi. Yeah. Yep, negative e to the pi times, well, I already took care of the negative 1. Negative 1 times e to the pi. E to the pi times negative 1. So then, my integral from 0 to pi of f dot dr is just f of 0 negative e to the pi minus f of 0, 1. And then I just plug all that stuff in. So this looks like 0 plus 0 minus a negative e to the 3 pi. Since if I cube e to the pi, I'll get e to the 3 pi. Minus on the other side, this looks like 0 plus 0 minus 1 cubed. Keep trying to match up where some of these pieces came from. And this one looks nice enough to simplify. Let's call it e to the 3 pi. E to the 3 pi plus 1. All right, I was promising what I hope is a slightly easier way of coming up with that potential function. So let me try that in the next example. And I also kind of did it in the first example we had as well, but I was trying to just jump around a bit. But let's just go back over it. I'd like to integrate p dx. And I'll get, just write out what it is there. This is the integral of, I think we had 3 plus 2xy dx, which is 3x plus x squared y. I'll also just go over and integrate q dy. Right, try to just directly undo the gradient in both parts. So this is the integral of, we had x squared minus 3y squared dy, which is going to be x squared y minus y cubed. So my function should be just picking out all of the pieces that show up in either of those two integrals. And I'm just leaving off the plus c's right now because they're just gonna get in the way. So if I go through my x integral, I get a 3x there. I get a plus y x squared y. Going over to the y integral where I see I've gone a little bit too fast again. Hey, don't take the 2 with you. Stay over there. The integral of x squared should be x squared y. Right, that'd be helpful. But I've already got that x squared y in the function because I'm expecting anything that has both an x and a y in it to show up in both. So I already grabbed it from the x integral. I don't need it a second time from the y integral. So I'll just skip over that part for now and just add in a minus y cubed. If I'm looking at where all of these things are coming from, Putting them all back together. Again, I see that this green one, x squared y, appeared both times. So I only need it to show up once in the final product. Let's try that again. All right, so that's kind of my process for reconstructing this function. All right, just integrate both sides. Integrate the p part for x, integrate the q part for y, and then just build my function out of the unique pieces from both. You can always check this thing by taking the gradient of f and seeing that it goes back to your field. But oftentimes, we'll just take your word for it on claiming that you found this potential function. So I think that this method just is faster and easier and kind of keeps everything together. Whereas the other process, while more detailed, sometimes you can lose the forest and all that detail. That makes sense. And then hopefully I'll still have enough time to cover like 2 more bits here in the next like 3 minutes. One of these at least I think goes pretty quick. Example pi. Figure shows a curve C in a contour map of whatever that function is. I want to find the integral of grad f dot dr. And if I look at this contour curve over here, based on the way that the arrows are going, I can see that I am ending up here, but I am starting down here. My start, I'm going to call A. My end, I'm going to call B. Maybe let me just slide that out of the way so I can see the numbers on here. My end is along a contour plot of 50. My end is along a contour line of 10, which means that those are the function values at that point. Right? Anywhere along that level curve of 50 means that my function is equal to 50 at any point on that curve. Same thing with my starting point. Any point along that contour line is equal to 10. So if I just come back over here and look at doing f of b minus f of a, this is going to be 50 minus 10. Which is 40. Cool. So ideally, again, with this fundamental theorem, things go pretty quick. Now, for the real fun bit, it is a little bit of a look beyond this section, but I know there's like 1 or 2 web work problems that'll cover a 3D, 3 variable potential function. There's this bit out of the textbook, which I thought was kind of dry, so I rewrote it. So trying to find an example of a vector field that's conservative with all 3 vectors involved. I'm just going to tell you this field right here is conservative, one that's provided. There's a lot to write down here, so I'll again remind you can find all of my notes just on D2L, follow the link to where I put all this stuff and look it all up over there. But just like with our conservative vector field for 2 variables or 2 dimensions, we're expecting this field to be the result of some gradient. Meaning I want f to be f partial x, f partial y, f partial z in order. Meaning p, q, and r are supposed to represent f partial x, f partial y, and f partial z already having been done. And I think if you were going to get anything out of this example, it would be this page right here. I tried to organize it in a way that I hope is helpful. Because what I want to show is that each of the available second order mixed partial derivatives should be equal to each other. So I'm going to look at calculating fxy two different ways. Right, one is already starting from f partial x, which is q. The other is already starting from f partial y, which is q. And then taking the opposite derivatives and seeing if they're equal. So I do p partial x and I do q partial y. That's the exact calculation we were already doing for two space. It's just checking the x and the y partials when mixed up and done in a different order still result in the same thing. So I just need to do that 2 more times for xz and for yz. And I'm just checking these 3 ideas over here on the right. And since they're all equal, I can claim that I have a potential, or I have a conservative vector field. So then integrate all 3 and recombine them all. And that's the potential function I got. Ta-da! Cool. We are going to look at this a lot more when we return to chapter 16 after exam 3. So I'll leave it alone for now. I would not expect a 3-variable potential function to show up on exam 2, so don't worry about that part. Okay, bye, 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 bye. Bye, 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 bye.